All right, we're going to start with something small, something you might have at home, a little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee and we'll pull it back. And let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. And there you have it, Newton's second law of motion in action.
In his well-known book Principia Mathematica, Newton gave the 3 laws of motion, of which we have discussed the first one in the previous video, and if you want to have a look at it, there is a link in the description. And now is the time for the second law. Before we proceed to understand this law, we have to first look at a term on which the law primarily depends. Now, this is an English version of the book, but Newton wrote the book in Latin. Let's have a look at it. Before the laws, he gave some definitions. Our concern is the second one. Now, I don't know how to actually pronounce Latin, so I would say pardon me for that, but I'll tell you the meaning of what he's trying to say here. Just focus on the 3 words. First one, quantitas motus, which means the quantity of motion. The second one is velocitate, which is the velocity, of course. The third one is quantitate materia, which means the quantity of material. Now, according to Newton, there is a relation between these 3. The definition says that the quantity of motion of any moving body depends on the quantity of material in that body and the velocity with which it is moving. Now, the quantity of material is basically measured by mass, right? And the quantity of motion is given a name, which we call momentum. So in short, momentum depends on mass and velocity of a moving body. And that is why if we form an equation for it, it is actually equal to the product of mass and velocity of that object or that body. So P is equal to m times v, where v is the velocity, m is the mass, and of course P is the momentum. Now there is a question. What is going to happen if you try to change the momentum of the body? Newton's second law says that the rate of change of momentum of a body is directly proportional to the force applied. Read that statement once more. The rate of change of momentum of a body is directly proportional to the force applied, and this change in momentum takes place in the direction of the applied force. Now, if we formulate this statement, it can be written as F proportional to dP by dt, right? And if we move further, the equation reduces to F is equal to mass times dV by dt. Now, one information here. K is actually the constant of proportionality. And the way we define a force, we take its magnitude as 1 in terms of SI units. Alright? Now, what is dV by dt? It is actually the acceleration, correct? And that is why the whole equation boils down to F is equal to mass times acceleration. This is a very important equation which you will be using while solving the problems. For now, our primary concern is this equation or this formula, F proportional to dp by dt. According to this, if the magnitude of the change in momentum is large and the time taken for this change is less, then the magnitude of force applied will be large, right? This is the basic sense of equation, correct? And that is why this is true opposite way as well for the less amount of force, right? For example, if you punch on the wall with bare fist, you feel a large amount of force, right? But it doesn't happen if you are hitting a punching bag. Why does this happen? Let's see how Newton's second law explains it. In the first case, when your hand hits the wall, the momentum of your hand reduces to zero in a very, very less time. And that's why the force on your fist is larger. While in other case, when you hit the punching bag, it takes more time to compress the bag, and that's why the time taken to reduce the momentum to zero is more, because of which the force on your fist is very less. And that's the reason, right? Let's watch a demonstration. In the first case, the time taken by the egg to reduce its momentum to zero was very, very less. It happened almost instantaneously, and that is why there was a greater amount of force applied on the egg. So it broke. In the second case, as the bucket was filled with water, the momentum was reduced to zero in more time, and that is why there was a way lesser force on the egg. So it was safe, right? There are tons of examples around you for this formula, for this law. I'll tell you one more. In almost all the vehicles around you, you'll notice a spring-like instrument near the wheels. Do you know what they are? We call them shock absorbers. And let me tell you what is their role. Whenever a vehicle takes a jump on an uneven path, it gains some momentum in vertical direction. And when it falls back on the ground, the momentum reduces to zero instantaneously. And because of which, there is a large force on the person sitting inside. But because of the presence of shock absorbers, this doesn't happen. The spring takes time to compress, and therefore, the momentum doesn't fall to zero at once. It takes some amount of time, and so the person sitting inside don't feel the force. Interesting, right? Now let's look at our final and the most used equation. Force is equal to mass times acceleration. What can you deduce from this equation? Let's say we keep the force constant. Or in other words, we are applying the same amount of force on the objects of different masses. What is the difference you are going to observe in the motion of these two? It's very obvious from the equation, right? If the mass is less, then there will be more acceleration. If the mass is more, then there will be less acceleration, right? It's very simple, correct? And this is what explains the video clip with which we started. Have a look. Now if this video looks interesting to you, do like, share and subscribe, and yes, hit the bell icon for the notifications. Now if you have any doubt or queries, you can drop a mail at slidescreen@gmail.com.